This presentation examines the chi-square test for contingency table. This is a test that we use to determine if various notions are independent. So let's remind ourselves of one of the important rules regarding independence. If two events A and B are independent, then the probability of A and B equals the probability of A times the probability of B. In general, the rule, of course, is the probability of A and B is the probability of A times the probability of B given A. But in this discussion, we're going to assume that the two events are independent. So we're going to ask our question. We want to determine if gender and grade in a statistics class are independent. So we're going to start with some data. We have 18 men who earned a grade of A, 20 who earned a grade of B, 13 who earned a grade of C, 9 who earned a grade of D. 12 women earned a grade of A, 16 women earned a grade of B, 6 women earned a grade of C, and 6 women earned a grade of D. And the issue that we really want to ask ourselves is, are these notions independent? Did women get grades in a similar fashion than men, or do we see some sort of a gender issue that is causing a relationship between the two variables? So these are our observed numbers. That's going to be important for us as we move on. So we want to go ahead and construct the numbers in the margins. 18 plus 12 is 30, 20 plus 16 is 36, 13 and 6 is 19, 18, 12, 13 and 9 is 60. So in essence now I have the total number of men is 60, the total number of women is 40, 30 A's, 36 B's, 19 C's, 15 D's, and 100 total in the table. Next we're going to remove all the numbers in the interior, but keep the numbers that are serving as totals. And then we're going to ask ourselves, if these really were independent, if gender and grade were independent, what numbers would go in each of these 8 cells? So we're going to assume independence, and we're going to first look at man and A. So if it's independent, we'd have the probability of being a man, which is 60 out of 100, times the probability of getting an A, which is 30 out of 100. That would be our probability. Except, of course, we don't want probabilities in these cells, we want counts. So we would take the probability times the total number to go ahead and give us our expected count. So our expected count, which I call number, the number in man and A will be 60 out of 100 times 30 out of 100, that's our probability, times 100, which reduces to 60 times 30 over 100, or 18. Notice I could also have said 60, the row number, times 30, the column number, over 100, to give me 18 in that slot. Next, we're going to look at woman in C, so we're curious what number goes in this slot. The probability of being a woman is 40 out of 100. Probability of getting a C is 19 out of 100. And again, we don't want the probability there, we want a count. So we're going to take this probability and multiply it by the total number in the set. So 40 out of 100 times 19 out of 100 times 100, and again you'll notice the hundreds cancel. We just get 40 times 19 over 100, 7.6. 7.6 will go here, but also notice the pattern. 40 times 19 over 100, row number 40, times column number 19 over 100 will give me my expected count. My expected count there is 7.6. So here indeed is our rule to simplify. The number, or our expected count, will be the row total times the column total divided by the overall total, R times C over T. So if you look at men and B, men, row 60, column 36, total 100. 60 times 36 over 100, 21.6 for men and B. For men and C, 60 times 19 over 100, 11.4. Next up for men and D, men, 60 times 15 over 100, row time column divided by the total. Next we have women in A, women, 40, A, 30 over 100, 12 women in A. Women in B, row number 40 times 36 over 100, 14.4. And finally, women in D, 40 times 15 divided by 100. So these are all of the expected cells. If gender and grade were independent, these are the numbers that should have been in the table. Those are the numbers we would have expected if our variables were independent. So So again, these are expected counts. So we have our observed counts. These were the things we actually had seen, so we're putting those numbers back in. And now these are our expected counts, the numbers that we obtained by doing what? By determining the probabilities multiplied by the total, what we would expect to get if gender and grade were indeed going to be independent. So our test statistic here is a chi-square. The chi-square test statistic is the sum of the observed number minus the expected number squared divided by the expected number. So you can see here are our observed numbers. Notice no decimal points there. Here are our expected numbers. We have a few decimal points. And then here's our chi-square. Observed 18 minus 18. Notice if they were perfectly independent, we would have had 18 men, and that's exactly what we had. So observed minus expected, 18 minus 18 squared over expected over 18. The next one, observed 20, expected 21.6. 20 minus 21.6 squared divided by 21.6. And we have to continue like this for all of the cells in the matrix. So to assist us with the computation, let us go to Excel. So you notice my headers. I have observed, I have expected, and then observed minus expected squared divided by expected. So we're going to go first here, equals observed minus expected squared, observed minus expected squared divided by expected. And that, of course, is 0. Observed and expected are equal. Notice this next one, we observed 20, we expected 21.6, not very far off. So these numbers tell me how far off my observed number and my expected numbers were. And you can see they're all relatively close, which is indicative of the fact that it certainly may have been independent. Well, let's go ahead and get our test statistic. The test statistic is the sum of all these things. So if we add all these together, what do we get? We get 0.858. So our test statistic chi-square is 0.85. So we have our chi-square. Next we want to establish our null and alternate hypotheses. And we're not stating this formally, but we are getting at the idea behind this test. H0 will be row and column variables are independent. HA will be row and column variables are dependent. If they are dependent, there is a relationship. If women were more likely to do better than men, then it would be dependent. There would be a relationship between the variables. So what I would say in this context, for H0, I would say gender and course grade are independent. One does not affect, influence, or tell us anything about the other, versus related. If we reject H0, if we throw H0 out, then we're going to say gender and course grade are related. And the only way we're going to throw H0 out is if the observed and expecteds are very different from each other, which is not what we saw in this case. Okay, next up we're going to look at our degrees of freedom. For this test, the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So we usually write that as df equals r minus 1 times c minus 1. In this case, what did we have? Now, do not look at the totals. Our raw data, we had 2 rows, men and women, 2 categories. Our columns, we had 4 columns, A, B, C, D. So plugging that into our formula, 2 minus 1, 4 minus 1, we get 3 degrees of freedom. So we know our test statistic and we know our degree of freedom, and what do we do next? Well, we have to draw a chi-square. Notice if the chi-square was exactly 0, then all of the observed and expecteds would be exactly the same. So that certainly is reasonable to be independent. It's perfect in a sense. When the expected and the observed deviate, then the chi-square number gets larger. So the larger the chi-square, the more evidence there is to throw out H0 to show that there is a relationship. So this is always going to be a one-tailed test. We are only going to determine the area to the right of the test statistic. You'll notice I have my graph of a chi-square with 3 degrees of freedom. 0.858 is way over here, and we have 0.8355 is the area to the right of that. And again, this is a one-tailed test to the right. 8355 will be our p-value. If you'd like to try that, the applet to do the computation is at the bottom of the slide. So our p-value here is 0.8355. what does that mean? If gender and course grade were completely independent, what are the chances to get a data set like I have, or worse in some sense, where there's a greater relationship just by a random chance, and 84%? Well, that means that there's a pretty good chance this could have been independent. But we're not going to say except H0. We're not going to say H0 is true. What are we going to say instead? Indeed, we're going to say fail to reject H0. The p-value is large, which means there is insufficient evidence to claim that gender and course are related. They may be independent. That doesn't mean they are independent. We don't have enough evidence to say they're not independent, so they may be. We cannot be sure. Okay, Minitab can also do the computation for us, so let's quickly go over there and see how Minitab would solve this problem. So you'll notice I've put all of the observed values in C1, C2, C3, and C4. A, B, C, D across the top, men and women would be the rows. The command on Minitab is just CHISQ. So we're going to type that in, CHISQ. It's going to be a chi-square. Where is my data? C1 through C4. And then we'll let Minitab show us what the results of that will be. What do we get? You'll notice we get an entire matrix. We have expected counts are printed below observed counts. So observed 18, 20, 13, 9, 12, 16, 6, and 6. The expected numbers 18, 21.6, 11.49, 12, 14.4, 7.66. The number underneath is going to be observed minus expected squared divided by expected. Then if we add all those together, we get our chi-square statistic here, which is 0.858. Here's our degrees of freedom, which is 3, and then our p-value here, which is 0.836. And of course, if the p-value is large, we fail to reject H0, and that agrees with what we said earlier. And that will complete this presentation.